Have you ever actually stopped to think about how supercomputers can predict global weather patterns in just a matter of minutes? Or how giant cloud applications manage to handle millions of complex requests all at once without completely crashing? Well, today, we're going to demystify the absolute magic behind supercomputing and large-scale distributed systems. Welcome to this explainer on high-performance computing, where we're going to really look closely at the architecture of divide and conquer.
Okay, let's dive right in by looking at the fundamental problem we are trying to solve here. For a really long time, computing relied entirely on sequential execution. This is where you just have one processor tackling tasks one by one. And sure, it's incredibly simple to program, but it is painfully slow for massive tasks. If you have an algorithm with an O of n squared time complexity, throwing a huge dataset at it will practically freeze your machine. So what's the solution? Parallel execution. By utilizing multiple processors, we definitely require much more complex parallel hardware, but the payoff is absolutely massive. We can take that exact same O of n squared time complexity and slash it all the way down to just O of n. It's really the ultimate solution to that single-core bottleneck. To wrap our heads around this massive topic, we've structured this explainer into 5 logical steps. First, we'll look at the need for parallel computing. Number 2, the muscle, CUDA and GPUs. 3, the playbook, which is parallel algorithms. 4, the nervous system, or communication strategies. And finally, number 5, the manager, Kubernetes orchestration. All right, kicking things off with Section 1, the need for parallel computing, breaking the bottleneck. Look, modern computing tasks, things like deep learning, crunching massive big data sets, or running heavy scientific simulations, they literally cannot wait around for sequential execution. It's just not an option. But when we build these massive parallel systems to handle them, we need a solid way to measure if we're actually succeeding. The absolute key performance metric in high-performance computing is called speedup. Speedup measures the actual real-world improvement you get from parallelism, and it's calculated very simply. Just take your sequential time and divide it by your parallel time. So if a program takes 10 hours sequentially but only 1 hour in parallel, your speedup is 10. Our ultimate goal here is to drastically lower the execution time to reach what we call cost optimality. That's the sweet spot where a parallel system uses all of its resources efficiently without wasting any processing power whatsoever. Moving right along to Section 2, the muscle, CUDA and GPUs, powering the computation. Think of it this way. If a CPU is a single, highly skilled master chef, a GPU is more like a massive commercial kitchen packed with 1,000 average line cooks, all working at the exact same time. To actually put those 1,000 cooks to work efficiently, we use CUDA. That stands for Compute Unified Device Architecture. It's NVIDIA's parallel computing platform, and it essentially gives us the framework to run our programs on the GPU for massive, high-speed computation. Now, CUDA organizes this potential chaos brilliantly using a strict hierarchy of grids, blocks, and threads. A grid contains many blocks, and a block contains a group of threads. And because a thread is the smallest possible unit of execution, this whole architecture allows us to execute thousands of individual tasks at the exact same time. And guys, this isn't just some theoretical lab concept. This hardware architecture is quite literally the driving force behind the modern digital world. Without CUDA's high-speed processing, we simply would not have today's artificial intelligence or deep learning models. Things like advanced image processing, video rendering, predicting complex global weather patterns, and even life-saving medical imaging, they all completely rely on this massive parallelism. So how does a program actually execute all of this? Well, it follows this incredibly beautiful 7-step choreography between the host, which is your CPU, and the device, which is your GPU. Let's walk through it. First, you allocate memory on the host. Second, you allocate memory on the device. Third, you copy your data from the CPU right over to the GPU. Fourth, the CPU launches the kernel. Now, the kernel is just a function that gets executed in parallel by many GPU threads. Step 5, the GPU actually executes those threads. Sixth, you copy the final result back from the GPU to the CPU. And finally, step 7, you free the memory. It is a completely perfect handoff of instructions. Which brings us to Section 3, the playbook, parallel algorithms, instructions for the muscle. Raw muscle is pretty useless without a playbook, right? When you have thousands of processors working all at once, you really have to ask yourself, how do they avoid stepping on each other's toes? This introduces a huge concept called parallel overheads. See, if your processors spend all their time just talking to each other, synchronizing data, or waiting for their turn to access memory, the whole system grinds to a halt. We call this overhead, and managing it is the core, absolute biggest challenge of writing parallel algorithms.
We solve this potential chaos by balancing something called granularity. Granularity is basically the amount of work assigned to a processor before it needs to stop and communicate. Fine-grained parallelism breaks tasks into tiny little pieces. That's great for dividing the workload, but it requires really frequent communication and high synchronization. On the flip side, coarse-grained parallelism assigns huge chunks of work. This means way less communication and often better efficiency. But there is a catch. If the tasks are too fine, communication overhead just ruins your performance. If they're too coarse, some processors finish early and just sit around idle. So balancing this granularity is exactly how we prevent load imbalances.
Let's look at a very specific playbook maneuver here, the odd-even transposition sort. This is a parallel algorithm for sorting data. It's essentially a parallel version of the classic bubble sort. But instead of going one by one, processors simultaneously compare adjacent pairs of numbers. In the even phase, it compares pairs starting at even indices, so 0 and 1, then 2 and 3. Then, in the odd phase, it switches and compares pairs starting at odd indices, like 1 and 2, then 3 and 4. By doing this simultaneously across multiple processors, it slashes the overall time complexity from a sluggish O of n squared all the way down to a super fast O of n. It's brilliant.
All right, moving into section 4, the nervous system, communication strategies, sharing the data. Because once our processors are crunching numbers, they still need a way to actually share their results with each other. And the physical speed at which they share this data is entirely dictated by the network topology. For instance, a ring topology connects nodes in a literal circle. It's super simple to build, but data has a really long path to travel. A mesh topology uses a grid. It's much faster and highly reliable, but it gets expensive and complex. But the real crown jewel here, that's the hypercube. This connects nodes in a binary cube structure where adjacent nodes differ by just 1 bit. It is incredibly complex to actually build, but it's wildly efficient, bringing communication time down to O of log p. Now, these physical network topologies are what allow us to execute complex communication operations, and one absolutely critical operation is the one-to-all broadcast. This is where one single node needs to send identical data to every other node in the entire network. To do this quickly, we use a trick called recursive doubling. Basically, the root node sends the data to one other node. Then, both of those nodes send it to 2 more. Then those 4 send it to 4 more, and so on. The information spreads exponentially, like wildfire. We also use operations like scatter to distribute different chunks of data, and gather to collect all the results back to a single root node. When we're working in massive clusters, we typically program these communications using MPI, the message passing interface. And as developers, we have a major choice to make here. We can use blocking communication, like the MPI_send command. This is where a process completely stops working and just waits until the communication finishes. Simple to code, but very slow. Or we can use non-blocking communication, like MPI_ISend. With this, the process fires off the data transfer and immediately goes right back to computing without waiting around. By overlapping our computation with our communication, we prevent those costly idle times and massively boost our overall performance.
And finally, that brings us to section 5, the manager. Kubernetes orchestration, running the show.
Look, when you are running enterprise AI, processing big data, or managing global cloud applications, you aren't just using one computer. You are relying on massive clusters of thousands of machines running containerized applications. Enter Kubernetes. Kubernetes is an open-source framework originally developed by Google that perfectly orchestrates all of this chaos without any human intervention. If web traffic suddenly spikes, Kubernetes uses auto-scaling to instantly add more containers. If a server node completely crashes, its self-healing feature just automatically restarts the workload somewhere else. It completely handles load balancing and automated deployments, making it the absolute ultimate manager of distributed computing. But, here is the really crucial point we have to understand. Despite all of this mind-blowing technology, we still face very real theoretical physical limits in high-performance computing. And this limit is defined by Amdahl's law. Amdahl's law essentially states that the sequential fraction of a program, meaning the part of the code that simply cannot be parallelized, sets a hard, unbreakable limit on your maximum speedup. So let's say just 5% of your code absolutely must run sequentially. Well, it doesn't matter if you add 10 processors or 10 million processors. Your speedup will never, ever exceed 20 times. That tiny sequential part will always, always become the ultimate bottleneck. Which really leaves us with this final kind of provocative thought. In this rapidly accelerating age of AI, are we actually going to hit the hard ceiling of Amdahl's law?
Or will we end up relying on Gustafson's law, which argues that as our computing power increases, we'll simply scale up the massive size of our problems, allowing our hyperclusters to essentially scale infinitely? The physical limits of tomorrow's parallel computing networks are literally being tested right now as we speak. And grasping this architecture is absolutely key to understanding where the future of technology is headed. Thank you so much for joining me on this explainer. I really hope this helped clear up the incredible invisible systems running behind the scenes of our digital world.